If we in the UK were not previously aware of Iceland's volcanoes, then last year changed all that, as the eruption of a volcano whose name I will not dare to pronounce before a native speaker closed airspace all the way across Europe and left people stranded in departure lounges, including our speaker, in fact. In fact, Iceland is one of the world's most active volcanic regions, with up to 20 eruption events producing up to 5.5 cubic kilometres of magma every 100 years. And here to tell us more about his native country's violent geology is Dr. Thor Thordarson, reader in physical volcanology and natural hazards at the University of Edinburgh. Thor has studied Icelandic volcanoes for over 25 years and has researched the physical volcanology of effusive and explosive eruptions, including their environmental and climatic effects. He is in fact the world's leading expert on the 1783-84 Laki-Fisher eruption, with 23 papers published on its various aspects. His current research centres on historic and Holocene volcanism, with particular emphasis on explosive eruptions at active central volcanoes in Iceland, including the one that went off last year, and sits on the British government's scientific advisory committees on Icelandic volcanic ash emergencies. And I still don't know whether we had one of those before last year. Maybe Thor will tell us. Ladies and gentlemen, please welcome Dr. Thor Thordarson.
Thank you, Ted, for this wonderful introduction, and I also would like to thank the Geological Society for actually inviting me to come here. I'm both honored and privileged to actually be here and have the opportunity to talk about volcanism in Iceland. I wish I could say that all of what I'm going to tell you is based on what I've done, but it's not. There's a lot of people involved, and a lot of good people have contributed to this. But hopefully I can give you a good overview of the nature of volcanism in Iceland, and what I want to focus on tonight is particularly the explosive side of things. I am going to keep the theme of the lecture more or less within the confines of the island of Iceland, not venture too much off the island. It might maybe disappoint some, but I'm not going to talk much about the atmospheric effects in Europe and its consequences. And there is good reason for that. There's probably people better than I in giving you all the details about those aspects. I'm very comfortable with volcanism in Iceland since I spent a lot of time studying it. But also is that in the discussion associated with the effects and the impact of last year's eruption, there have been quite often some kind of misleading statements made about the volcanism in Iceland. And it seems to me that people need a little bit more information about what the nature of volcanism is, be more clear about the differences in different types of explosive eruptions, and hopefully I can provide some insights into that tonight. Iceland features a lot of explosive eruptions, but explosive eruption is not necessarily the same as an explosive eruption. There's a lot of difference, both in terms of their intensity and their style, and we need to take that into account when we're actually assessing the far-field, potential far-field effects of those events. So, tonight I'm going to start with a little bit of outline of geology of Iceland. Hopefully I won't spend too much time on it. Just sort of give you an idea of what underpins volcanism in Iceland. Get into a little bit about post-glacial volcanism and magmatism, some facts about that. But the principle or the core of this talk will center on Icelandic eruptions, or particularly explosive eruptions, and I will try to do that by examples, including the last year's eruption of Eyjafjallajökull. Now you know how to pronounce it, right? Anyway, so this slide is just put up there just to remind me to tell you about the reason why Iceland is actually above sea level. Now, the total area of Iceland is 103,000 square kilometers. It's a part of a much bigger basaltic plateau. A large part of it is actually submerged, or about two-thirds of it is actually beneath sea level. And it's situated on the mid-Atlantic ridge system, and you can sort of see even from this satellite image here the lineaments of the tectonic trends here, which actually delineate the rift comes across here, and unfortunately the continuation of it is under clouds. It's very difficult to get a satellite image of Iceland without clouds. And so it is part of the mid-Atlantic ridge system, but then the question is, why is it the only subaerial part of it? Well, the reason is that it also is part of a much older and more extensive system, which is usually referred to as the North Atlantic volcanic province, which extends here from the Disco Island of Greenland to the UK. So the tertiary basalts in the Scottish Islands, the Hebrides, and the basalts of Disco Island, and also on the east coast of Greenland, which were produced about 60 million or 60 to 56 million years ago, represent the initial stages of this province, and Iceland simply is the modern day active part of that system. It's a system that's been active more or less for 60 million years, and the reason for all this activity is a mantle anomaly. Someone call it thermal anomaly, I'll call it mantle plume. It depends on who you talk to. So there's a mantle plume underneath Iceland, and that actually has created a buoyancy to this part of the ridge system. So the superposition of the ridge onto this mantle plume is the reason why Iceland rises 3,000 meters above the surrounding seafloor. And as you can see, the rift of the ridge is here, comes across Iceland, becomes quite complicated as you go into Iceland, and the reason for that complication is the ridge is trying to stay on top of the mantle plume, so there's a relative movement between the mantle plume and the ridge. Now, which one is moving? Is it only the ridge that is moving, or is it both? We don't know yet. Very well, this is a geological map of Iceland, much more simple than the geological map of the UK. And basically, three major formations. Iceland is a very young structure. What you see above sea level is younger than 16 million years. The initiation of the formation of the Icelandic basaltic plateau is thought to have happened about 25 million years ago. But on the surface, so we do this grouping very easily. The tertiary basalt formation extends from 60 million years to 3.3 million years. And then we have the Plioplastocene formation, which is roughly from 3 million years to 0.7 million years, and the upper Pleistocene formation, which is everything younger than 700,000 years. And if you look at the distribution of those, the tertiary formation, or all the basalts and volcanics of the tertiary, are on either flank of Iceland, east and west side. And then we have the Plioplastocene sort of following this red line here along the Iceland, which is actually the rift axis across Iceland. And the youngest rocks basically follow the axis, are sitting basically on the axis. So the geology of Iceland is very much controlled by the activity on the rift system. And the distribution of formations mirrors that. And the rift system, as it is today, it consists of numerous volcanic zones, the Reykjanes volcanic belt here, Western volcanic zone, Northern volcanic zone, complicated a little bit by this zone here, which is referred to as the Eastern volcanic zone, which is younger than 3 million years old, and represents or was formed as a propagation through all the crust to the southwest, and it's basically gradually taking over the Western volcanic zone. This is what people refer to as rift jumps. So activity is shifting this way. Interestingly enough, the Northern volcanic zone used to be located over here, and about 7 million years ago it actually jumped to its current position. And this, in a way, complicates the geology of Iceland a little bit, but not too much. Also, there are, on either side, there are nature fracture zones or transform zones, the Tjörnes fracture zone and the South Iceland seismic zone, which are basically transform belts that connect Iceland to the mid-ocean ridge. And this is just showing where the propagating tip is of the Eastern volcanic zone. So this is actively propagating here. Eyjafjallajökull is right there. And here we have actually better developed drift. I just put this one up just to illustrate one point really, and that is to explain the dip of sequences in Iceland. I mean, I can spend quite a lot of time talking about it. It's actually quite interesting and a useful model that was produced by Pálmason in 1973, and explains a lot of the features in geological features in Iceland, but not all of them. But it nicely explains the reason for the inland dip that you see generally in sequence in Iceland. If you look at the northern volcanic zone here, see on either side of it, everything is dipping towards the rift zone or the volcanic zone. And the reason for that is because the loading of new material in the active volcanic zone, it's going to be highest towards the center of the volcanic zone, and towards its margins, it's going to be less. And this loading causes the rocks that actually get buried, they will actually be buried along a path that goes almost straight down in the central part of the volcanic zone, whereas those who produce further out, they will actually have a much shallower burial. But at the same time, this loading will cause things to dip inwards, just simply from sacking of the crust on either side of the rifts. And that gets preserved throughout. Complications and turnarounds in the dips just reflect older positions of the volcanic zones prior to them jumping into the current position. Now there are a series of rock suites or magma suites in Iceland. The most prominent one is the Tholitic one, which dominates the rift, as you will see on the next slide. But we also have alkalic rock suites, which are very characteristic of certain volcanic systems and volcanic belts in Iceland. And between the two, we have what we refer to as transitional rock series, which is very characteristic in the sense that it's typically in the basaltic end, it's more alkalic. As you get to the more silicic end, it has a tendency to shift over towards the oleic characteristics. The distinction between these things are based here on total alkalis versus silica, but it also shows up in a number of other elements, in particular incompatible trace elements, where the alkalics are usually more richer in those elements than the tholiites, and tholiites are generally depleted. So this is a distribution of the rock types. Tholiites typically formed in the active rift, even in the northern part of the eastern volcanic zone. But when you get to the tip of the eastern volcanic zone, where the propagation is taking place, you have transitional alkalic volcanism. And so in the intraplate volcanic belt, or the flank zones, as some people refer to them as, you have alkalic volcanism. And main reason for the alkalic volcanism is thought to be the degree of partial melting that generates the magmas that erupt here is less than what it is in the rift systems, which are generally produced by a fairly high degree of partial melt. But there are other differences. So, and this circle here actually represents, it's based on geophysical estimates, I guess I should say, rather than measurements, where the center of the Mantle plume is. One of the characteristic features of the geology of Iceland are the volcanic systems. And they're very simply defined as a fissure swarm, surface fracture systems basically, and sometimes they have central volcanoes associated with them, and a lot of them do. So basically, if this is associated with a central volcano and the fissure swarm, and the way people map them out, you have fairly elongate systems where you have concentration of fractures and fissures and a central volcano, which defines this geological identity, which is also identifiable in the tertiary sequences on either side. In the tertiary sequences, they appear as dike swarms, as was demonstrated by the work of George Walker in eastern Iceland from 1954 to 65. But the way people actually try to define these things, that's not clear. Some people draw these according to the distribution of the fractures. Some people will draw them in accordance to the magma compositions or the magma that produced by system and claim that each system has a distinctive chemical signature. That is true for some of them, but not true for all of them. And also worth noticing is that this is particularly true out here, where you actually have a lot of volcanic systems which are dominantly or dominated by fissure swarms and are all very chemically similar. So they're not distinct by chemistry, but these are basically distribution of surface structures that are used here to draw them up. Things get a bit more complicated when you get up here, where the delineation between different systems based on surface structures becomes very difficult. So it is a bit difficult to say what is a classical or useful definition of a volcanic system. But what we do know is that when we have had events, both in historical time, is that in those events, these individual systems will be activated. And what I mean by that is that you will have a volcano-tectonic episode, which will feature drifting, reasonably localized drifting, and spreading. And associated with that, you have usually volcanic eruptions, and that seems to be confined to a particular system at any one time. So each system experiences a volcano-tectonic episode every 300 to 400 years or so, on average. Another thing to notice here is that we got 30 active volcanic systems in Iceland, which basically means that we got, in a simple way, we got 30 active volcanoes in Iceland. So plenty to take from. Now, in terms of those volcanic tectonic episodes, here, this sketch here is just to demonstrate this association of a volcanic central volcano and the fissure swarms. And in those cases, if you have a volcano-tectonic episode, you will actually activate the whole system, including the central volcano. The difference between what's happening out here versus what's happening out there is better probably explained on the coming slide, but sort of features also in here. The central volcano, which is usually thought to be low-Q activity for these volcanic systems, has a shallow magma chamber, but also a deeper magma source. Whether you want to call it a chamber or reservoir or whatever you want to call it, but there is usually some feature underneath. Geophysical measurements show that its activity at the central volcano cannot be explained by a single shallow magma chamber. But there is a shallow magma chamber, usually at depth of 3 to 4 kilometers beneath the volcano, which explains why you have this low-Q activity there, because you will have very frequent eruptions from those things. You only need to pressurize it a little bit to actually cause it to erupt. And your frequent eruption will build up an edifice. Further out here, we don't have the shallow magma chamber, but you have a much deeper source for the magmas. At least that's one explanation, possible explanation. But out here you also have typically eruption, which we refer to as monogenetic. And they typically have fusive eruptions, lava-producing eruptions, and they're typically basaltic in composition. This contrast in the central volcano, which are polygenetic volcanoes, where you actually have well-defined and formed conduit system, will erupt over and over again on time scales of several 100,000 years, and will produce the central volcano. Activity there can be effusive, explosive, and it produces a range of magma compositions, from low silica basalt to high silica, silica rhyolites. One of the characteristic features, one of the characteristic features of the system is that when you have a volcano-tectonic episode taking place, is that the central volcano and the fissure swarm are active at the same time. They could erupt near simultaneously in time, so that you will have an episode that lasts maybe for a decade, activating both systems. And one of the more better known examples of that is the Krafla 1975 to 84 volcano-tectonic episode, which activated the Krafla central volcano as well as the fissure swarm. And that actually led to this hypothesis of that the central volcanoes represent where the magma is actually coming up from the mantle. So they are actually the pathway where magma rises up towards the surface, accumulates in a shallow magma chamber, and there's a pressurization of that magma chamber that causes things to erupt when the pressure, when it overcomes the lithostatic load around it. The pressure is enough to actually force magma up to the surface through the central volcano, but also feed out lateral magma along a lateral pathways or dikes that will produce fissure eruptions out on the fissure swarm. One of the things that inevitably comes out from this model, and one of the things that the conclusion you can draw from this model, is that the driving mechanism of the drifting is the actually emplacement of the magma. So it actually is coupled to magma injection. The rifting is coupled to magma injection. And recent measurements, geologic measurements in Iceland, show that actually spreading in Iceland is a continuous process. It does not happen in episodes. It's not an episodic thing, it actually is continuous. And most likely the reason why we have this rifting episode on these systems is that you build up stress within the crust, and as you split it out, it will fail along certain segments, and hence the rifting episode on those systems. So this is a little bit of a, even though this is explains some of the features that were observed in the Krafla fires, it doesn't explain all of them. One of the features that it explains very nicely was that you have earthquake swarms that propagate away from the central volcano and outwards and seem to, in time, correlate very well with activity within the caldera and out there. But it doesn't explain the fact that when these magmas erupted, the magma that came up within the central volcano or in the caldera was very low magnesium basalt, about 5% weight magnesium, whereas the basalt that came out through fissures right outside of the caldera was high magnesium basalt, up to 7 weight%. So either you, in that case, either you have a stratified shallow magma chamber and you're tapping different portions of it in the same eruption, along the same fissure, and you have this some kind of boundary right where you have the caldera fault, or you're tapping two different sources, one deeper and one shallower. Anyway, so there are caveats in this one, and that led August Guðmundsson to come up with a bit more elaborate model for these events. He argued that the fissure swarms were actually a surface expression of a much larger magma reservoir sitting close to the crust mantle boundary, and it was inflation in that deeper reservoir that actually caused all the rifting and formation of the fissure swarms. And as magma rises up from that deeper reservoir, sometimes it would actually hit the shallow magma chamber underneath the central volcano and force magma out of that one, causing eruptions at the central volcano at the same time. Both of these models are, have very useful components to them. And for a long time, I actually really favored August's model. I thought that actually explained a lot of the features, until we started actually looking at a particular volcano in northern Iceland, the volcanic system, Askja volcanic system in northern Iceland, and we started to find things that didn't comply with either of those models, which led us to come up with this one. This, in a very short, illustrates that the magmatism associated with these volcano-tectonic episodes is actually decoupled from the tectonism. Magma just comes up because the rifting actually opens a pathway for magma, which at that time happens to be ready to erupt. So whatever happens coming up on the central volcano is actually unrelated to what is coming up out on the fissure swarm. The reason for that is is this difference in chemistry. If you look at a little bit more detail of the Askja 1874 to 1876, should be volcano-tectonic episode. If you just look at the basalt, this volcano-tectonic episode produced not only rifting but eruptions that took place over this period of time. Probably the best known of that is the rhyolite explosive eruption from Askja in 1875, which took place on the 28th to 29th of March. But that eruption was preceded by basaltic eruptions in this time period. And in 1875, out on the fissure zone, both to the north and the south, there were some products out there. There was basaltic fissure eruptions out there, and namely the 1875 Holocene and the 1875 Sveinagja. So these two eruptions here took place very close to the main explosive Silicic eruption which took place at the central volcano. And based on that, number of researchers put forward the idea that this was all related to the lateral flow theory. So Sveinagja and Holocene came up here and then were ejected laterally from the shallow magma chamber, which fed the fissures out there. Chemistry does not comply with that. Clearly, Holocene is very different from the basalt that actually came up right before the Silicic eruption in Askja. And looking at this ratio, the niobium-zirconium ratio versus zirconium, tells you that these cannot be explained in a way that they come from a common source. They must be from different sources. And because this ratio here remains unchanged during crystal fractionation. Also, Sveinagja, which plots up there along with some 20th century Askja central volcano products, quite similar in composition in that regard, but they're very different. And by the same token, these cannot be generated by crystal fractionation, because if they were, then this ratio should be the same, it would be unchanged. Possibly they might be explained by mixing. So you have something which has somewhat higher niobium-zirconium ratio and still higher zirconium, maybe silicic melt, and you mix that with this basalt to produce that. That doesn't work either, at least not for the Askja rhyolites, because if you look at the niobium-zirconium ratio for Askja rhyolites produced at the same time, it's much, much lower. It should plot up there if it was a part of the mixing product. So, in conclusion, is that even though we can't say anything definite, it looks to me that the eruptions, the magma that comes up in those eruptions associated with the volcano-tectonic episodes is not, well, it's a consequence of the rifting. It's decoupled from it in the sense it doesn't really partake in the rifting episode. It just comes up because you open up a pathway. It's just a passive infilling, really, of cracks that are opened up by the spreading. Well, turning the shift a little bit, let's look at some statistics on Holocene volcanism and magmatism in Iceland. This table here just basically shows the number of eruptions, both effusive and explosive. And I want to focus your attention on the explosive side of things. And this is our best estimate of the number of explosive eruptions that have taken place in Iceland since the glacier retreated, basically for the last 11,000 years or so. Total of 2,400 eruptions, roughly. So a lot of eruptions. One of the reasons why we have so many explosive eruptions is the fact that a lot of both the volcanic systems and the central volcanoes that are most active today and have been most active in the last 10,000 years, they are actually capped by glaciers or covered by glaciers. So when basaltic magma comes up, which normally would erupt as a lava flow and did so in the Tertiary, produced all these numerous lava flows that we have, they interact with the glaciers that produce meltwater, and that meltwater interacts with the magma and produces an explosive eruption. And at the end of the day, what you have is a lot of explosive eruptions, most of them basaltic, and interestingly enough, the young propagating rift zone, eastern volcanism, is the most productive in terms of number of eruptions, by far. About 95% of all eruptions that are taking place in Iceland in the last 10,000 years come from the eastern volcanic zone, the propagating one. I don't have a very good explanation for that, why, but that's what the records are telling us. Same thing actually applies in terms of production, magma production. And if you look at distribution in terms of composition of the magma that is erupted, you can see in all cases the basaltic end dominates things, and silicic magma is produced at fairly low rate, but although in a quite significant rate. I also should state that Iceland actually features quite a high number of silicic eruptions compared to most active systems on Earth. The number of silicic eruptions in Iceland is very close to be the same as for New Zealand, which is one of the most prolific producers of silicic eruptions that we have today. But I should also stress, that's just the number of eruptions. That does not apply to magma production, because Iceland, silicic magma production in Iceland is much lower than in those systems. Just some nice photos of central volcanoes in Iceland. The top one is Eyjafjallajökull, and it gets the top seat because that's where Jules Verne had the journey to the center of the Earth starting. So they actually went down there. It's probably also one of the best examples of a stratovolcano in Iceland. Most of the central volcanoes in Iceland don't fall under that category. And only the central volcanoes in the flank zones actually can be regarded as typical stratovolcanoes. And Eyjafjallajökull is one of them. This one here, Eyjafjallajökull, which is in the tip of the propagating rift, is probably the best example of the example of a central volcano in the rift zone, though. It is a shield volcano, very similar to, in its construct, to actually the shield volcanoes in Hawaii. And most of the central volcanoes in the active rift in Iceland are actually shield volcanoes rather than stratovolcanoes. They're a little bit modified by the fact that a lot of them have been constructed by subglacial activity. Öreefajökull is another well-known, and we'll come back to that one on the next slide, I believe. Typical caldera volcanoes like Askja, this is the 1875 Askja caldera, which is actually nested in a much bigger caldera. We find a few of those in Iceland, and then of course we have the famous Hekla volcano, which is difficult to classify because when you look at it from the northeast or the southwest, it looks like a typical, archetypical stratovolcano. It has the morphology exactly of that. If you look at it from directions which are perpendicular to that, it looks like a boat that it turns upside down. And the reason for that is, in every eruption, either some crater will erupt in the initial phase, but it's subsequently followed by opening of a fissure along the crest of the volcano, which is up to 5 kilometers long. And this happens over and over again. And that's why the shape of Hekla is as it is. Now, just another set of pretty pictures of monogenetic volcanoes, which characterize the fissure swarms. So these are actually volcanoes produced by just single eruption, and they will not erupt again. And we can divide them sort of roughly into those produced by very long fissures and those produced by very short fissures. The short fissure ones have a lot of different types. You have all types of volcanoes that you can think of really in those things. But sort of archetypical types are the spatter cones, like Elborg, the scoria cones of, for example, of the 1973 eruption at Eldfell in Heimaey, and of course tooth cones, which are here represented by the Hverfjall, or the crater mountain at Lake Mývatn. A nice, very circular crater primarily made out of ash. Another very spectacular feature of those monogenetic ones with a central vent are the lava shields. These are not, they're different from the shield volcanoes in the sense that they are monogenetic, even though the shape is very, very similar. And these have a central vent, which usually is filled with a lava lake, which feeds lava out to the sides. These are actually really large volcanoes. They have volumes up to between 15 and 30 cubic kilometers, and they're up to 800 meters high. And they're produced by very prolonged eruptions that can last for decades or even hundreds of years. Very similar to the activity that is currently underway at Kilauea volcano, the Puuokupaina eruption that's been going on since 1983. So, but they are nature constructs, and it's I've always found it amazing that an eruption can actually produce its own mountain in that shape in just one eruption. Now the linear fissures, there's several types of them. There's the Eldgjá type here, and those are fissures that actually have featured a lot of what we call fountain-fed lava flows. They don't have big vent ramparts. This is actually the Eldgjá chasm itself. It's not produced in this eruption. It's actually the older structure, a tectonic structure. The fissure just took advantage of it, but it never really produced any reasonable crater ramparts because it was violent enough that material, any pyroclastic material, was actually dispersed away from the vents. And the fountain-fed lavas basically flowed away as quickly as they were formed. This is contrasted with Laki, which actually is delineated. We have really well-formed cones, spatter cones and scoria cones. And in this case, you had initially, at the beginning of each episode, eruption episode, you had powerful explosive phase. This was short-lived, usually about a few hours, and was followed by activity of declining intensity, and as the activity declined, we actually built up cones. The larger the cones are, the weaker the explosive activity is. And then, of course, we have fissures that actually came in encounter with surface water, lake, filling in lakes, and those produce ferromagmatic eruptions and are lined by what we call ash cones, a series of ash cones, very low aspect ratio cones, the really wide craters. The record of explosive activity in Iceland is very extensive. Written records go back to the start of the settlement in roughly about 874. But, of course, as you go further back in time, the quality of those written records decreases significantly. But we actually have, back to about 1600 AD, we have actually really good records which more or less document every event. And some of them documented in such a way that they describe day by day what happened during particular eruptions. A very useful record. But history in Iceland is not that long. It's only 1130 years or so. So we need different ways of doing this, and we're very fortunate that when you go to soil profiles or any soil sections in Iceland, you will find a lot of ash layers in the soil. And basically this soil records, has tephra layers which record basically the past history of explosive volcanism. It's not a perfect record, but it's a very, very good one. And we now have added to this by studying lake deposits, or tephra layers in lake deposits. So we have almost a complete record of tephra layers back to 11,000 years that are preserved either in soil or lake deposit sediments. And that's actually quite a unique record, but it also gives you a wonderful tool to work with when you're looking at explosive eruption. Styles of activity, very simplistically. We have dry explosive eruptions where the magma rises to the surface. As it decompresses, the gases escape, magma starts to recirculate, and as a consequence of that recirculation, the magma column expands and you have an explosive eruption on your hand. So it's all driven by the gases that were originally dissolved in the magma. And these produce actually relatively coarse-grained fault deposits, something like you see right there. And so the fragmentation is not very efficient in these ones, even though they might be powerful in dispersing material long distance. The other case is wet or ferromagmatic ones. Of course, magma that is formed in those things, as it is rising towards the surface, it undergoes the same decompression, it goes and starts to recirculate, and etc., etc. But an added component is actually external water. And if you get that external water into contact with the magma, that results in flash boiling of the water, which expands. That actually drives effective interaction between the magma and the water, and as a result, you have actually an explosive eruption, and the products of that one usually have a lot amount of high quantities of ash. Just a few words about silicic explosive eruptions. This plot here, I should probably explain that a little bit, because we will have few of them showing up in the next few slides. So it's basically thickness on a log scale here plotted against square root of area. And the square root of area is basically a very useful measure of the equivalent radius for each deposit. So it gives you a measure of how far it would go if there was no wind. So you can actually correct things if distribution is skewed by wind. So it gives you an idea of how far these deposits go, basically. And you can see the most powerful explosive eruptions, the silicic ones, like Askja, the Öreefajökull, they're all up here, and they have fairly wide dispersal. And the area underneath these curves is basically a very good measure of the total volume that is produced by these eruptions. So you can use this plot actually to calculate out how much magma was coming out of the volcano. And if you look at some of the basaltic end members here, the Vatnord, which are the ash cone fissure that I showed you earlier, Laki and Eldgjá, they do have quite a impressive dispersal in terms of the tephra they produce, specifically Eldgjá, which was quite explosive, but not anywhere close to the silicic explosive one. So, and it's very tempting to use this plot to infer about intensity of the eruption based on this. But we've got to be very careful because, for example, in deposits like Eldgjá or even Laki, they are extensive eruptions which feature multiple explosive phases, and which were formed over periods of months or even years. And then you look at it in the field, those, depending on the dispersal, if it all went in the same direction, each episode will add to the thickness of the deposit, make it more impressive in that way. Or if it dispersed in different directions, they will actually increase the effective dispersal of the deposit. because one is going east and one is going west at particular times, whereas most of these very explosive ones, like Öreefajökull, is an eruption that lasts maybe for 3 or 4 hours. And all that material is coming up very shortly, and it's dispersed downwind, and it's just one event of tephra deposition, whereas the other ones are multiple events of tephra deposition. So when you're doing that, you have to be sure that you're actually comparing events that have only one event of tephra deposition to an event that has the same characteristics. You can't compare events that have multiple, one event of tephra deposition versus multiple events of tephra deposition, because that would give you, skew the image of, make these more powerful, really, the one with the multiple. Anyway, so, high number of silicic eruptions. This number is always changing. I mean, every time I give a lecture, I always have to change that number because we're finding new and new tephra layers, silicic tephra layers. So we're actually getting closer probably to 65, 70 now. They need to be confirmed, so that's why I didn't put them up. But these numbers is changing as we get better and better record. And this is a lot of silicic explosive eruptions. A lot of them actually send ash to Europe, as a matter of fact. And they're Plinian type eruptions, or ferroplinian type eruption when you have external water interacting with things. One example of these eruptions is Öræfajökull 1362, which is the biggest explosive eruption in Europe in the last 2,000 years. It's bigger than Vesuvius, 79. And it actually caused some significant damage in Iceland and effect, and we'll get to that. But if you look at it, we're kind of lucky here. Iceland was actually quite lucky in this eruption because the winds were favorable. It all went to mostly to the east, and most of the tephra was actually deposited into the sea or carried over to Europe. And you do find that deposit actually in peat bogs, for example, and lake deposits in Europe. And if you compare it to Pinatubo, in the 1991 Pinatubo eruption, which is shown the dispersal, or the outline of the eruption cloud from Pinatubo is shown here, to superimposed on Iceland and Öreefajökull. Pinatubo produced a very big mushroom cloud with a radius of 200 kilometers. Öreefajökull produced not quite as impressive one, but we know from the fallout right here that actually it traveled up to 100 kilometers upwind. So it's quite a powerful eruption, probably of the plume that extended beyond 30 kilometers. And it is fairly large volume. It's approaching the dense-rock volume of Pinatubo, so it's quite a big eruption. Produced quite impressive deposits as well. Here is the inferred wet site, and these two sites here are, this one up here is on the south flank of the volcano, and that's this pile here of tephra, or deposits that were produced by the eruption. Most of that actually is cross-bedded tephra, which suggests that most of it was emplaced by pyroclastic density currents. So it's a big pyroclastic density current. If you go further down, the same density currents are actually here, but much thinner, just a few centimeters thick. But it's kind of an important thing to actually recognize this, and this was not recognized until we started looking at it, this deposit a few years ago, because these pyroclastic density currents will travel with enormous velocity, up to 200 meters per second, and they're charged with hot gas as long as with the tephra. Anything in their way is going to be killed. And a lot of it could be destroyed. And one of the reasons why people get killed in those is the heat, but the other thing is they are deprived of oxygen. But they traveled, these things, we know they traveled at least 12 kilometers from source. They might have traveled further. And why is this important? Well, if you go back into the historical records, you can read about the effects of this eruption on the community surrounding the volcano. Some people have questions of records, but what we are finding is actually adding support to those records, which state that in this area here there were between 35 and 40 farms. So it was actually a very prosperous farming community, and up to 400 people might have lived there, which is actually quite a high population density for that time. And the record states also that all of those people were killed. Now, people have excavated the ruins in two places, one at Gröf and one at Bæ, from this eruption, And in the older one, you can actually see the pyroclastic density current deposited plastering onto the walls of the ruins here. And here you can see, in this case here, if you, well, you can't see it, but if you dig down here, you can actually see the pyroclastic density current underneath there and actually filling in part of this. But this is all the fault deposit on top, and this is the remnant of the roof. So one way to interpret this is actually the fault deposit was on the roof. The roof didn't collapse immediately, but collapsed later on. The reason why I go into this detail is because when you go into these ruins, you don't find any evidence of people or any artifacts. See, everything, you know, and people have said, well, no one was killed because they must have removed the whole things and escaped. I don't think so. You have to, when you're looking at this, you have to take into account that the eruption started early in the morning, just before 9 o'clock in early June. And most people would have been out in the fields working. And if that's the case, and you had this pyroclastic density current coming down, they could have basically killed everyone out in the fields, and you would have very few people actually in the farm. So that would explain why there's no people there. But why are there no artifacts? Well, if those buildings were still standing after the eruption, even though they, you know, the surges went over the place and the fallout came afterwards, but the structure was still standing, the area is totally devastated. People could have gone in and cleaned out those things because who was going to use them there? Might as well take them and use them somewhere else. So what suggestion is that this eruption really wiped out that community in South Iceland at that time. Of course, a lot of Icelandic tephra layers, they actually dispersed quite a distance. Some of them actually go all the way to Europe. And here's two examples. This is Askja 1875, which produced tephra fall in Scandinavia and Germany. This is a 12,000-year-old vet tephra, which is even more impressive distribution in terms of impact in the far field. Some large basaltic eruptions. These here are magmatic eruptions induced by interaction of magma with surface water, in this case a lake, and produced tephra layers that cover almost half of Iceland. Thought to be very powerful explosive eruptions, but we might have to rethink that a little bit in the light of the most recent eruption, Eyjafjallajökull, and also because there's a possibility that there might have been multiple asphalt events associated with these eruptions, which are giving you an indication of more explosive nature than actually it was. Now on to subglacial eruptions. Very briefly here, basically what happens here is that when the magma comes up and the hot gases that escape from it, they actually melt the ice, they melt a cauldron into the ice, and that produces a lake of water that actually, the standing water that actually accumulates into that cauldron. And as more magma comes up, that interacts with that water and generates a ferromagmatic eruption, which results usually in some construct like this, or like that one, where you have standing water in the cauldron and you build up a subaqueous cone construct, and you produce ferromagmatic explosive eruptions that will produce fallout and pyroclastic density currents. This here is the typical sequence that you actually find when you're actually mapping out what we call subglacial volcanics. The stuff that is deposited on the ice is never preserved in the geological record, but our study of the 2004 Greenswell eruption suggests that actually material on the ice constitutes half of what is erupted. So there's a lot of history in here that we lose in terms of the records of the eruption. Most of the subglacial eruptions in Iceland are basaltic, or 60% of all the events, and they are actually typically very small, moderate volume, and suggestions are also that they're actually of moderate to weak intensity compared to the more silicic ones. If you look at that plot there, just notice the scale difference here. That's 700 kilometers and that's 300. This photograph here is of Katla 1918. An old photo. A few words about the 2004 eruption. This one also actually caused disruption to aviation. It sent plume north, as you can see here. It was a short-lived event, lasted only for about 4 days. And the NASA research plane was actually flying north of Iceland and inadvertently flew straight into the plume, and it caused quite a bit of damage to the engines, but they also got very good samples. And this eruption actually produced a number of quite interesting things, interesting deposits. And I'm not going to, because I'm running out of time, I'm not going to spend time on this. But what you see in these deposits are pumice lenses interacting with a lot of fine ash. And in the past, we've had a hard time interpreting this, why you get these really basaltic pumice-rich layers intercalated in this nature with the ash. And the answer actually came in 2004. It basically means that you had simultaneous emplacement of deposit by pyroclastic density current and fallout. Where the pumice lenses come from the fallout, and most of the ash comes from the pyroclastic density currents. Also, more importantly, in these kind of events, you produce a lot of fine ash. More than 20% of the material is less than 63 microns, and majority of the material is actually less than 1 millimeter, or actually less than with medium mass and down. And this is interesting in the context of the recent eruption. Past ferromagmatic eruptions in Iceland have been much bigger than what we see in present day. This one is 10K saxonite tephra, which came from Greensweden as well, and sent tephra ash to Greenland and to Europe. And people looked at this, have usually considered this to be a single event. Our records have demonstrated that is not quite correct. It's actually 5 events, and I show 3 of them here, but they're very closely spaced in time. Some of them sent ash to Greenland, and others sent ash to Europe. Now, just a few words about the Eyjafjallajökull eruption. I'm more or less presenting here things that is a collective effort of many, many people, and all these names here constitute the Iceland/University of Edinburgh eruption team. Eyjafjallajökull is, of course, there, and it was preceded by unrest, which started in 1994. That's quite an important thing, and significant events in 1999 as well, and early 2009, and things really escalated towards 2010. Up till 20th of March, when we had this small flank eruption here to the east of the Eyjafjallajökull, small basaltic eruption, effusive eruption, and that one lasted to 12th of April. I actually was there in Iceland during that period of time, and by the 11th I decided, well, that's enough, I'll go back to Edinburgh. And, so I flew back to Edinburgh, and just to realize that I had to return a few days later when the summit eruption started on 14th of April. It took me quite a bit of time to actually get back. It wasn't as easy as I thought it would be. But interesting thing is that in the first day of this eruption, there was quite a bit of melting that took place as the magma came up within the summit caldera, forming several cauldrons, and they were sending jökulhlaups or flash floods down either flank of the volcano. And most people have referred to this initial phase as being ferromagmatic. I have a little bit of not so sure about that. I'm not sure that is the right way to express that, because in the last jökulhlaup deposit to come down here, we find these rafts on the surface, which are actually pumice, very coarse, as millimeter to centimeter size pumices of the same composition as has been erupted by the volcano, and which is suggesting basically that the initial phase of this eruption was magmatic, produced actually by expansion of magmatic volatiles. One possible explanation for that is the water that was produced by the initial melting was dislodged very effectively by the jökulhlaup, and by the time the magma came up, this area was effectively dry. Someone was really, really angry when that screamed quite a bit, I think. Several eruptive phases in the eruption. We don't have much time to go in detail, but I've avoided to give those things volcanological terminology. I'll just call them initial, middle, and final, because we still have to determine what style of activity characterized each period. But the initial phase, quite explosive, with frequent explosions of, which look like being volcanic, a series of volcanium-type explosions, fairly high magma discharge. This was followed by 19 days of very low magma discharge and primarily lava effusion. Activity picked up again right around the 3rd of May, increasing discharge and renewal of volcanic explosions. It was in this time when ash was sent to Europe. So this caused the main closures, initial closures of the airport, and then it happened again here. Look at plume heights. We won't dwell much on this. They are certainly associated with these estimates, but what they basically tell us is that the plumes due to this eruption were fairly low, most of them below 7 kilometers. They're confined to the troposphere, despite the fact that this eruption produced wide dispersal of ash. And it also goes to tell us that we should not ignore eruptions that are confined to the troposphere when we look at far distal effects. Clearly they can actually send ash and other things several thousand kilometers away from the source. They don't have to have a stratospheric injection to do that. That's the key element there. Total mass that is erupted, but very small, 0.17 cubic kilometers of dense rock, very similar to what Mount St. Helens produced in its time. Even though Mount St. Helens did that over a few hours, this one did this over periods of several weeks. Most of the material was deposited in and around Iceland. Only 20% of the material was actually dispersed much beyond 200 kilometers in Iceland. We'll skip that. We'll go there. This is a map just showing the distribution of ash in Iceland. Here are the main ashfall deposit and main dispersal directions. This is the main direction here, which sent plumes to Europe. And there's another one went straight south of the volcano, as you can see here on the 17th. And one of the characteristic features of this is that both of these plumes sent significant amount of ash to Europe. This one going south and curving back into going straight over the UK. And it did contain, 20%, roughly 15-20% of fine ash which was sitting in that plume is significant. And the reason why it had so much so much material is because the ash was incredibly fine-grained. So you can see from this car driving down the road about 55 kilometers to the east of the volcano. This is a predicted dispersal for that plume. This dark area is supposed to represent concentration. I wouldn't take them too seriously. Actually, we don't exactly know how much the concentration was in that. But so this event produced really widespread deposits. And on the 19th, the only flight out of the UK, which actually I caught, went to Iceland. went to Reykjavik. It was the only flight out of the whole of UK on that day. Everything else was closed. Like I said earlier, a lot of fine-grained ash. We don't have the whole deposit grain size yet for this eruption, but even just a few tens of kilometers away from source, all of the ash is actually really fine-grained. It's very, very fine ash. It's below 125 microns. That's falling out of the plume. So we know that most of the really coarse material fell right around the vent areas, and a lot of fine material was dispersed away from the volcano. And these are just pictures showing what the ash looks like. These four here are from 14 and 17 in Iceland. Take a note of these aggregates here. Scale about is 10 microns, but it's actually a lot of fine material. So a lot of grains actually in here are less than a micron. This is aggregate that fell in Germany. This is what fell in UK. Some of these things are very, very delicate things. I still don't understand how that gets preserved. I can understand how it's formed, but I don't understand how it gets preserved. Someone was very happy with his achievement because he was actually puffing cigar smokes out of it. Fortunate to have the eruption happen in the wintertime. Very, very cold though, but the snowfalls actually provides you with a very useful way of separating out individual explosive phases, so you can actually date events very accurately. A lot of aggregates falling out, both hailstones with ash and also just accretion lapilli. The deposit very close to the vent is quite thick. A lot of interesting things, but we have very high resolution records of it, so that will enable us to actually decipher this and get some really good information out of it in terms of eruption style and conduit processes. And I've spoken far too long. Just the final word is, Eyjafjallajökull is not the first and will not be the last eruption to send ash to Europe. We know of 8 to 10 incidents in historic time of ash being dispersed from Icelandic eruptions to Europe. That's just what we know. There's probably more of them. And in the last 10,000 years, there's quite a few, probably over 50 of them that actually have sent ash to Europe. So that's just to take some note of it. inevitably we will actually have to deal with this again at some stage. Thank you.
Well, thank you very much, Thor. We have time for just a few very brief questions. So if you would like to put your hands up if you have a question, and if I pick you, could you please wait for the microphone to arrive? This is not so that we can hear you so much as the recording can hear you. So, are there any questions? Gentleman down the front here.
Thank you very much. You showed three theories of the origin of the eruptions and also in the fault lines. The bottom one showed, I think, two different sources for the eruption in your picture. Now, what is the difference in time between it occurring in one and another? I know it was 5 kilometers on your horizontal scale, but are they two different sources? And if so, how is it they erupt or it within a very short period of time?
Mm-hmm. Well, they are, in terms of time, these events are happening almost simultaneously. They might not necessarily be, in terms of scales of day, but in terms of a year, they happen within the same year. And so, in that sense, we're talking, yeah. And but they are two different magma sources, as our chemistry suggests anyway, that they come from magmas that are not directly related. So that's why we have them, separate like that. And reason for that, I think, we still need to demonstrate it, and we need to work on this a bit more. But the idea, at least that we're working with, is that you will have a rifting episode, a tectonic episode on those systems, and you're actually opening up cracks. And if you have magma sitting below, and irrespective of where it exactly is, but it's very close to be ready to actually erupt or migrate towards the surface, the rifting episode actually just opens up a crack that allows it to come up and fills in those cracks. So where we don't have an eruption, there was no magma there that was ready to actually move up. But where you had eruptions, it was ready. Is that?
Just a quick one. Any recent ideas on how jet engines could be protected or shielded through the atmosphere, particular atmosphere? Because at the moment, after an eruption, of course, it's several days before any aircraft can fly through. So has there been any thoughts or ideas or structures or concepts on the protection of jet engines?
I think you have to ask those who actually manufacture them about that. I don't think there is much you can do in terms of shielding the engines themselves. But what you can do is make them more adapted to actually dealing with the ash itself. In the sense that, as I understand it, I'm not a specialist on this by no means, but what happens when the ash goes into the jet engine, it's very high temperature there, you melt, at least partially melt the ash, and that makes it stick to the blades, the turbine blades, and that, and that actually stops the engines. As the engine cools down a little bit, then you actually weaken that remelted tephra, and and sometimes you can, so far they've been able to restart the engines because of that. And I think they're actually looking at, I don't know whether it's because of design or how you respond to it. General response of a pilot in that case would be to basically put thrusters on full, which will increase the temperature, which will increase the melting of the ash. And people have suggested that the correct response would be actually to reduce it and lower the temperature in the engines. This is what I understand, but I have to stress that I'm not a specialist in that aspect. And I don't think it's very difficult to actually design something to prevent the ash to get into the engine, because the engine needs air through it, otherwise it won't won't
Thank
work.
you.
One last question down the front.
My question was also similarly to do with the ash and engines. And I mean, does it make a difference, the size of the particles and the silica content? Would that also make a difference, you know, what they're flying through? Because, I mean, we all know that bird strikes are not a good thing for aeroplanes. Birds are quite big, but is there a size element, and is there a you know, like a silica element or a content element of the ash that would make a difference to the engines being able to fly through it?
Yeah, if you think about it, does. I mean, only we have to just think about the simple fact that silicic magma melts at lower temperature than basaltic magma.
Yeah.
So that obviously will make a difference in terms of how readily those ash particles will be remelted as they enter the engine. Things that we also need to think about in terms of size is the size will matter as well, and the shape of the particle will matter as well. So some of them are very rugged, some of them are fairly equal with smooth outer surfaces. And all of those things will also contribute to the way the particles actually melt and react with the engines. Another element in there is also gas content, especially anything that has been already converted into acid, so sulfuric acid, hydrochloric acid, and the corrosive effects of those. And that's a concern for the engine, but it's also a concern for other instruments and air intakes, for example, on airplanes, if you fly through Plume. So it's a reasonably complex issue, and you have to think about a lot of things. It's not only the gas and the engine, it's also other aspects of it that we need to think about as well. But
sounds like a fruitful field for the engine engineers and volcanologists to get together.
absolutely, and I think that's happening as we speak, but we also have to remember that it's kind of difficult to get the manufacturers to go into collaborations, open collaborations like that, because as I understand it, the temperature that the engines operate on is one of their big industrial secrets and differs between these manufacturers. So if you give that away, then you're actually giving away your, very precious.
Well, ladies and gentlemen, before we pass through into the all-important reception, I must thank on your behalf Thor for giving us so much to think about when we're sitting on our bags at Heathrow.
Thank you so much. Thank you.